Dots. Season pencils. That's what the company is called. The company is called. Yeah.
Is this what we're doing now? I don't get one now. It's going down. Everyone's painting so.
Oh, that would be amazing. Amazing. Name.
Right. Are we ready to roll?
WW.
Are we ready? New year, new lesson. Yes. Everybody, fingers crossed for a little snow and not gross ice. That would be nice, wouldn't it? I would very much enjoy it if we got a little bit of snow. Oh man, yeah. How much snow?
Well, we got, I'm thinking it'll be good by Sunday, but there's a bunch of kids doing gymnastics on Saturday that aren't going to be doing it, I'm afraid. We shall see. We're doing it Sunday. All right, so lesson 18, get your notes out. Be sure you're ready. So states and state changes.
Oregon.
Oregon, Minnesota. Oh,
Lucy left.
What do we do with the
Don't
have
quarter
in it, right?
What?
Well,
What is so?
so what would happen if somebody forgot to put quarter three in their binder?
oh, then you're just guessing on your own today, I guess. Trying to figure it out. Hopefully you at least did it and you can remember an answer. Handful of coins. All right. So states and state changes. Wait a minute, we've talked about this like back at the first day. Okay, but now what we're doing is we're talking about it from an enthalpy entropy standpoint. So it is a little different than just basic states and states matter, but we have to review them to make sure they make sense. So the particles in a solid, how are they oriented? What do we say? They have what? Yes. Fixed position. That's right. And liquid particles can move easily past one another. Liquid forces lead to what characteristics? What things do we see with liquids, forces in liquids? Caitlin? Yep. No defined shape, but defined volume. What else do liquids do? Surface tension, that's one. Yep. But they also have surface wetting and capillary action. Okay, this is my favorite question because I don't know the answer. If you take a goldfish and you put him in a tank, is he wet?
Yes.
Yes.
No.
If is the tank full of water,
Yeah.
then he's wet.
Is he wet?
Yeah.
So when you're under the water, are you wet?
Yeah.
When you get out of the pool, are you wet?
Yeah.
Yeah.
But you're in the water, are you wet?
Yeah. If you have an addict, if you
So everybody agrees that if you're in water, you're wet?
No.
See, no, there's always people that don't agree.
if you have an abnormal amount of green, if you have an abnormal amount of water on you, then you are wet.
This is more like a philosophy question. Caitlin. Okay, wait. Caitlin put her hand up.
I thought you were talking about the snack that Smiley's had.
Oh, yes, those kind of goldfish will they will for sure get wet and gross. So I love that one. That's one to ponder. Okay, so surface wetting is pretty obvious, right? Like if you have a paper towel and you put a drop of water on it, it's going to be wet. It wets whatever the surface of something is wet if there's water on it. Capillary action. Capillary action is how water will wick through a material by filling all the tiny spaces. So if you have a drop of water on the counter and you just touch like the corner of a paper towel to it, you'll see it suck through the paper towel. Those are the water molecules clinging to one another and clinging to the sides of whatever little tunnels are in that paper towel and moving through it. Paper towels are designed to take advantage of capillary action.
Okay, just to clarify, we're saying if you just put a drop of water on a paper towel, the paper towel is wet.
I would agree.
Yes.
But, hang on. If you just drop the paper towel in a pool and like the paper towel goes under, now the paper towel's not wet.
No,
That's
it ain't
what
wet.
you guys were saying. man.
It's wet.
So how am I not wet if I jump in the pool?
You're wet.
You are wet when you jump in the pool.
People will argue, there are people who, you can find great, like, internet videos of people who will argue this, like, and get angry about it, about whether or not you're wet in the water, or you're just wet if you get out of the water, and now you're wet, you know? Wait, hang on, BJ, that's a good point. There you go. Back here, so PJ made a good point, maybe you just don't notice the wetness when you're submerged.
And like when you get out of the water, then you notice that it's wet.
Right.
Do not stress.
You still notice you're wet, like your hair's wet and.
You under the water.
This part can keep going. All right, hold on, gang, hold on, Drew.
Okay, think about it from this perspective.
No.
No. What did it say? So think about it from this perspective.
Yes.
And that's from the area that's wet, okay? How many water molecules of like vertically are there?
What?
Listen. Then, if your entire body is like, okay, even if it was just by one drop, are you still no longer wet? All you're doing is just increasing how tall it is.
You're not on something.
Okay, let's more. I'll take Asher.
Bro is not, bro is
Alright.
not on something.
Hold on, wait a minute, hold on. We're gonna do 4 more viewpoints. We got Asher, Andrew, Ridley, and Caden's opinion, and then we have to move on. Asher, your opinion on wetness.
Are we still dry underneath the water that's covering us? Cause that's all that's wet. so-
You're awfully wet on the inside, right?
Yeah.
That's a great question. Like, we're all pretty wet.
It's not in water.
I mean, like, let's say you have a.
Wait.
Let's say the drop of water in this counter.
Yes?
Is it ever still dry underneath the
Yes.
water?
Oh, that's a great question.
No, it's not. No.
What?
So he said if we put a drop of water on the counter, is the counter underneath the water dry or wet?
It's wet.
It's wet. Okay, Andrew, you?
Alright, so hear me out. You're never actually touching molecules. This
I
like,
no.
that's like
Not
so
going there. It's not. No. That is not.
Get out of the water. The water just stays on. It's because it has no water.
What do you see on somebody?
Okay, wait. Ridley?
Have the sensors to feel wet and feel cold from the water, so you never actually feel the water until
Nah.
You not feel the texture.
Smart.
We don't have the
Feel
sensors.
it. You didn't feel the water.
But we can
You feel cold.
You can feel this, you can feel water on you.
It's a matter.
You can feel water on you.
Okay. No, and then we gotta move on. Hang on. Wait, Drew, Katie, you're answering this question. Okay, what?
Gas particles are essentially wormholes.
There we go. That's where we're going. We're going here. Independent is where we're going. Okay, so one more thing on capillary action. If you've ever been to the doctor, they don't do it so much anymore. Now when they poke your finger, they use these little strips that they touch, but they used to use these glass tubes called capillary tubes, and they still do it sometimes for hemoglobin check. So what they do is they take that little teeny glass tube and they touch it to that drop of blood and it goes right up. And it does that because of surface tension and because of hydrogen bonding, and it's clinging to the sides in that glass tube and it shoots right up. And then they take that little glass tube and they put like a little bit of like putty or something on the bottom to close it up. And they put it in a centrifuge which separates all the parts of your blood because your blood is a mixture. And then they can count using a little measuring device how much red blood cells, white blood cells, and plasma you have. And that's how they tell if you're anemic, among other things. It's actually a really simple process. All right, so gas particles are independent. Moving on, we can do these together. Temperature, energy, and state. How does liquid go to gas? Liquid does what? Evaporates to gas. Gas condenses to liquid. Solids melt to liquids. Liquids freeze to solids. Solids sublimate to gas, and gas deposits, yes, to solids. There you go. It undergoes a deposition because has a court date, right? All right. So now we're going to talk about some intermolecular forces. We had that quick review. Oppositely charged ions attract each other. What kind of forces attract molecules to each other? As opposed to those that attract elements within a compound. So if you're attracting molecules, Caitlin, do you know?
Is it dipole?
That's one of them, but what do we call this whole umbrella of these types of, Jordan? Intermolecular. Very good. Okay. Intermolecular are between molecules. Forces that attract elements within a compound are what? Not sub. Intramolecular. Where does an interstate take you? From one state to another, right? It connects the states. It's an interstate. Ah, did you ever think of that before? Intermolecular forces. If you had a route number and you wanted to call it an intrastate highway, if it never left the highway, yes, it would be an intrastate, meaning it doesn't leave the state. So intramolecular forces are within the compound. Intermolecular forces are from different molecules of the same compound and what attracts them to one another. That's how compounds stay together, right? Otherwise, we would just have like one molecule of a substance and it would not be like a whole massive substance. You have to have some forces there. So one of these is dipole-dipole. So the positive end of one molecule attracts the negative end of a neighboring molecule. And what goes in this blank? Anybody know? Caitlin?
Is this dipole?
Yeah, this is dipole-dipole that we're talking about. So this is going to affect melting and boiling points. And you'll see why in just a little bit. The more polar a molecule, what does that do? If a molecule is more polar, how does that affect its dipole-dipole? PJ? Nope. Anybody? Yusuf? Yeah, the stronger, the greater the dipole-dipole. And then what happens to the boiling point? Caitlin? You know? She's taking a stab at it. Yeah. Yeah. I'm about to address that when she finishes answering. Give up. Trying.
The dipole forces
Mm-hmm.
definition.
Yep. Guys.
Wait.
She's doing good. I'll help you out. It's going to make it even higher. So the more polar a molecule, the greater the dipole-dipole, the higher the boiling point. Okay, you four over here. They don't even know I'm talking to them. You four over here. Not going to address it again. You're distracting other people, so don't. Don't make me separate you on day one. But next week, if you can't keep it together, find a new spot. Got it? Got it? Can we focus? Okay. Like mature people that we are semi-mature humans. All right. So hydrogen bonds. Where do these form? They form with electronegative atoms.
Hydrogen bond.
Are they stronger or weaker than dipole-dipole?
Weaker.
They're stronger than dipole-dipole. And they explain the unique properties of what substance? Where is this important? Water. Okay. Liquid water, is it more or less dense than solid water? Liquid water is more dense. Okay. This is why I've said before, hydrogen bonding is especially important to life on Earth. If we did not have hydrogen bonding in water, we wouldn't be here, because a lot of things that exist in our biosphere that make it possible to support life would not be a thing. When a pond freezes, the top freezes, right? You see the top is frozen, but the bottom stays liquid. All those creatures down there can continue to live. If it froze from the bottom up or in the middle, it would cause a problem, right? So this is also like, you've seen it. This is how ice works in a glass. You know, you have ice in the glass and it melts down, but your volume doesn't really change as long as your ice was all under the surface to begin with. It'll actually get a little less volume. And here's why. Because water moves around like this. Now, what happens when you heat up a substance? Does it expand or contract?
Yeah.
When you heat it up, it expands. When you cool it down, it contracts. Water does this to a point. When it hits its freezing point, it suddenly expands rapidly. So it goes from condensing to, and it's because it forms that particular
structure. Where it kind of yeah, it's very similar. It locks into place. And that's why ice is less dense than water, because it spreads out when it freezes. All right, so here's a little blurb on water. If it will go, come on. Here we are. Yeah.
Start things off. What never gets tired, no matter how long it runs? Comes from the natural world. It's the only natural substance on Earth found in all three common states of matter: liquid, gas or vapor, and solid, ice, which is another riddle. Unlike ice, almost all other substances behave like steel. When in liquid form, like molten steel, they're less dense than when in solid form. As steel changes from liquid cooling into a solid, say a steel beam, it condenses, concentrates, gets more compact.
The atoms coming closer to each other, and overall, the material becomes more dense, becomes more heavy for a given volume.
Drop the steel beam into the molten steel and it will sink. But drop a piece of solid water, ice, into liquid water, and whether it's ice cubes in your water glass or icebergs in the Arctic, it floats. In solid form, H2O is less dense, lighter than the same amount of H2O in liquid form. Because as you're about to see, when water freezes, it doesn't contract, it expands. Now, to puzzle out the riddle of ice, look at the H2O molecule itself. Two smaller atoms of hydrogen bonded to one larger atom of oxygen. H2O is a polar molecule. The same way our planet has two opposite poles, the H2O molecule has two polar opposite sides. One side has a slight positive charge, the other a slight negative charge. You've probably heard that opposites attract, so the slightly positive hydrogen side of every H2O molecule is going to attract and be attracted to all the slightly negative oxygen sides of other H2O molecules in all directions. These bonds, called hydrogen bonds, are what hold water together. And as you know, water flows easily. In liquid state, the H2O molecules are making and breaking those bonds constantly. Imagine massive numbers of H2O molecules in a hot dance club, dancing so closely and wildly that they're constantly making.
Yeah, looks like Mickey. Water looks like Mickey.
It's a lot of energy. They're not able to lock onto each other very well.
But watch what happens if the temperature drops. The energy level does too. The H2O molecules move more slowly, spaced further apart as if at arm's length. This is the water expanding as it freezes, which is at 0 degrees Celsius or 32 degrees Fahrenheit. That's water's freezing point, the temperature at which liquid water becomes solid water, ice. As the mass of H2O stops slam dancing and starts doing more of a molecular minuet, the water molecules are able to make longer lasting connections, hydrogen bonds, with each other. The molecules freeze in place, arms locked in six-sided or hexagonal groups that connect to form a 3D network called a crystal lattice.
Chemists will sometimes work weeks and months and years to get a single crystal of their compound or maybe a protein, and then you go by a frozen puddle and you can see one crystal of ice that might be 2 feet long, and it's just amazing.
This crystal lattice structure explains why H2O is less dense in solid than in liquid form. It's called water's density anomaly, by the way.
As you lock one water molecule to the next and the next and the next, you build up this network that actually has a lot of empty space.
All that empty space means there are far fewer H2O molecules in, say, a cup of ice than in a cup of water. Fewer molecules means it's less dense, which is why ice floats. But ice is no lightweight when it comes to strength. The Titanic only brushed past an iceberg on its fateful voyage in 1912, but that was enough to open fatal splits in the ship's steel hull. Water as it freezes expands with enough force to crack rock, burst pipes. Cutting through layers of ice can require axes, chainsaws, 3,000-ton ice breakers. As much as researchers know about ice, there are still unsolved riddles about what really happens on the surface of water and ice, about ice on other planets, moons, and asteroids. Think of this story as just the tip of the floating mass of H2O in solid form.
Couldn't resist that one, right? Okay, so if you want to have a fun experiment over the next couple days, because the next couple days are going to be very cold, you can take a soda can and a box and put it outside inside the box. Make sure it's a box that you can like lift like this, not have to open from the top. If you leave it out there overnight, the liquid in there is going to expand, but you also have gas under pressure. So it will explode. Who's accidentally left a soda in the freezer because you're trying to just cool it down real quick knows this. Yep, it will explode and it will make like these amazing stalactites of Coke or whatever because of all the bubbles, and as it freezes, it's kind of fun. Yeah.
You know,
Wait, I can't hear PJ and she had her hand up. Say it again.
Did you know, like, NASA scientists or something have found water on some of Jupiter's moons?
Yeah, they found water in all kinds of crazy places. Water's, yeah, it's pretty ubiquitous. So London dispersion forces exist between what kind of molecules? Non-polar molecules. And London dispersion forces, so we talked about dipole-dipole, now we're talking about London dispersion. London dispersion result from what? Temporary dipoles. What the heck is that? We're going to talk about that. So particle what and what play a role? Does anybody have this one? Particle size and shape are going to play a role. Okay, temporary dipoles. So we know what a dipole is. It's when you've got a polar molecule and it's attracting another one. Okay, this is the most ridiculous video I have found. It ended well. It started off like, what am I watching? But it explains what's going on pretty well if you just suspend many of your how shall I say, social expectations, modern social expectations, and just let this run. It's a little crazy. It's going to compare temporary dipoles to speed dating. Okay, so yeah, speed dating. It actually is a great analogy, but it's weird. It gets better at the end.
The most common but weakest intermolecular force is the London dispersion, also known as induced dipole force. London dispersion is a temporary attractive force resulting from momentary dipoles. They occur due to uneven electron distributions in neighboring molecules as they approach one another. Or they result from the weak attraction of the nuclei in one molecule for the electrons in the neighboring molecule. Let's put it this way. Pretend there's a restaurant hosting a speed dating event. Everyone gets the opportunity to get to know another person to find out if they have any mutual interest in each other. So a woman meets her first partner, and as they talk, there seems to be some attraction. But as time runs out, he leaves, and the attraction between them disappears. Interesting, probably. They talk, but there seems to be little or no attraction at all. Time's up, and one factor of attraction is solar mass. Let's say a wealthy man sits across from a woman. She becomes a lot more attracted to him because of his abundance of money. The woman mass here is represented by his wealth. Time runs out again, he leaves, and the attraction is gone.
Okay.
Now, the only benefit is all around short periods of time, just like the molecules of the dispersion. The molecules are moving around at a fast pace, quickly moving close to other molecules to form a brief attraction before moving on and repeating the cycle again. In many days, one realizes that she doesn't need anyone to make her happy, but she continues to mingle them.
It's better.
And just like how humans have attractions to others, molecules have that same attraction towards other molecules in a very, very close way.
So she was most
kind of wrapped up there.
yeah, most attracted to the wealthy guy. Whoop. But then in the end realized she doesn't need anybody else to make her happy. That's good. Okay, I appreciate that. All right, so but it's a good analogy of people bumping around the whole speed dating concept. There's attraction for a moment and then it makes sense. All right, so guys, get it under control. Seriously. Okay, melting. So this is a good graphic that's going to show you water melting, which is really kind of cool. But melting obviously is a change of a solid into a liquid when heat is applied. In pure crystalline solid, the process occurs at a fixed temperature called a melting point. And impure solid generally melts over a range of temperatures below the melting point of the principal component. So if it's a mixture, you got to go below the melting point of one of the larger components. But if you've ever wondered what melting ice looks like on a molecular level, it looks like this. So you can see this, look, we're applying heat energy. So they're starting to get jiggly and they can't hold on to each other for very long. It's a nice little graphic here. Woohoo! Wiggle around. Now they're wiggling a little faster. Ooh, it's exciting. It's like everybody was asleep and now they're turning on the music and waking everybody up so they can start dancing. And as they gain more energy and start to jiggle, they can't maintain that attractive force, that hydrogen bond. They're not close enough to each other for long enough for it to be as tight. So now that's all that's holding them together. That the little hydrogen bonds are holding them together rather than being the tight dipole. So there they go. And now you've got liquid water. So then next, if that was melting, come on and go to the next slide. Why are you? So freezing is when you got your process going through the changes from liquid to solid. So all the liquids except helium undergo freezing when a temperature becomes sufficiently cold. We can't get helium cold enough. But this is good because it actually had audio too. Somebody had fun with this. Ice. This is water turning to ice. Woo! And that's exactly how it happens, right? Like if you have a piece of ice, it will grow, right? It's not like it's going to form everywhere. It attaches to the one that already exists. And another fun thing you can do over the next couple days that takes advantage of that exact idea that they're latching on to ones that are already in the crystal lattice is if you take a bucket outside and you fill it up with, if you fill it up with cold water, your result's going to be kind of cloudy. But if you fill it up with hot water when you put it outside, you actually get a nice clear product. But if you put it out there overnight, it shouldn't be enough to freeze the whole bucket, but you can, tap a hole in the middle and pour out the water, and then you can make a little lantern. Have you seen that? You put the little candle inside at night or a battery operated LED candle, you get a nice little ice lantern. It's really kind of cool. But that's because they're sticking to what's already in solid form. All right, evaporation. Obviously, this is liquid to solid, but what's happening here is you're having more collisions. And as the collisions increase, because because the heat is increasing, the energy is increasing, the collisions are increasing, and they're literally kind of knocking each other out of place. And remember, there's vaporization and evaporation, boiling.
In the liquid phase, particles still stay together because of strong intermolecular force. As we add more and more heat, vibration of particles starts dominating, and at boiling point, it takes over the molecular force. As a result, liquid particles become free to move around and liquid sparks becoming gas. This process is also called vaporization. Vaporization of liquid takes place on addition of heat and at temperature above the boiling point. You must have tried your cloth in sunny days. In India, maximum temperature during summer goes around 40 to 45 degrees centigrade, which is way below than boiling point of water. But water disappears from our clothes when kept in sunlight. Have you wondered how this happens?
Have you?
Water disappears from our clothes way below 100 degrees centigrade because of evaporation. To understand it, let's analyze the top layer of water in a glass. Water particles on top layer have no water particles above them and they are loosely attached compared to particles at depth. After gaining sufficient energy, these surface molecules sometimes detaches from surface and become free. Sometimes collision of air particles detach them from surface. As they detach, they become free and become part of air. Such way of conversion from liquid to gas is called evaporation. Our clothes gets dry because of evaporation. Water level in pond and lakes gets reduced because of evaporation. Sweat from our skin gets dry because of evaporation. As sweat molecules are removed from skin, new sweat particles come out and bring heat with them. While sweating, you must have felt cold in front of a fan. This happens because sweat gets evaporated fast, which results in fast heat loss from body. You must have seen that under the fan, clothes dry fast. This happens because fast-moving air particles collide with water particles on surface of clothes and remove them from cloth.
So you've got vaporization, evaporation, and boiling. Vaporization is defined as what? Jordan, were you gonna tell me? What's vaporization, Gabe? You got a hand?
That's where water turns to vapor.
Water is liquid to gas. It's a phase change, a state change. Remember, vaporization is liquid to gas. What's evaporation? Yeah.
Evaporation is gas to a liquid. No, I sorry.
Liquid to gas, but specifically is evaporation is a type of vaporization that involves only the surface. Boiling is a type of vaporization that takes place throughout the liquid. So boiling is throughout the liquid, evaporation is only the surface. Both are vaporization, right? Why do fans help? What's the fan doing, James? You're sign languaging me.
It pushes the heat off of you.
Blowing the top layer of the water molecules, the ones that are only attached on the bottom, they don't have buddies all around them. They've only got buddies underneath, right? So they're more able to be tossed away. So that's what's happening. They're getting tossed away, right? Moved into the air. All right, so this is a good one. This will be helpful for you. So a gas to a liquid is condensation, right? And it's a reaction in which two or more molecules combine to form a larger molecule. We know this. This is review. While this occurs in many reactions, the term is usually reserved for reactions in which a new carbon-carbon bond is formed. So you will hear condensation used in a different way when you're talking about a chemical reaction. If you're talking about a physical change, condensation is simply you've got, gas changing phase to liquid. But when you're talking about chemical reactions, you will hear condensation used when you have a carbon-carbon bond. Kind of like we'll use hydrate in chemistry a little differently than you would use it in your day-to-day conversation. Okay, who's ever been in the car and the windows are all fogged up in the inside? Not icy, but fogged, right? Sometimes they're icy too. All right, they're icy if it's cold enough, but if it's cool, you tend to get the fog, right? PJ, you okay?
Yeah, sorry.
Okay. All right, so this is scientifically tested ways to get your windows to defog or defrost. Okay, and there's lots of methods, but you probably recognize the dude doing it. If you don't, I don't know where you've been for the last 20 years.
Some cars have a single button to defrost all the windows, but a lot of cars have controls that look like these. Since you're in a hurry, the question becomes, what optimal combination of settings will defog the windows quickest? Lots of people blast the windshield with hot air, but what if you use cold air? And should you be using recirculated air or air from outside? And does pushing the AC button or cracking the windows help speed things up? And if so, by how much? Recently, I had a disagreement with some friends about which combination of settings is best from a scientific standpoint. And if you look online, there are a bunch of different theories from self-proclaimed experts. So as a firm believer in the scientific method, I decided to test out my hypothesis. So for the past 10 mornings, with the help of some trusted friends, I've created a consistent environment to test all the different combinations and then document and rank the results. And the punchline is, I found there is in fact a specific combination of settings that will defog your windows in less than half the time.
Somehow he sounds younger.
I also stumbled upon some additional tricks that can make a big difference. But before I reveal the best settings, let's get some understanding as to why they're the best settings by quickly reviewing the science behind what makes a window fog up in the first place. For starters, I think it's common knowledge that if you zoom way in, the fog on your windshield is just little droplets of water we call condensation. And it's the exact same effect you see on a cold can or in a shower mirror, dew in the morning, your breath on a cold day, and even the clouds in the sky. All air around us has at least some moisture in it that you can't see, called water vapor. The higher the humidity, the more of this invisible water vapor that you've got. And as soon as you get anything beyond 100% humidity, it's too much. And that's when it clumps together and forms these visible droplets that we call condensation. Now, what's interesting is in a simple sense, hot air can hold a lot more moisture than cold air. In fact, at sea level, if this cube here had air at 103 degrees Fahrenheit that was fully saturated at 100% humidity, it would max out at 53 milliliters of water. But if that same cube contained cold air at 36 degrees Fahrenheit, it could hold a maximum of 5 milliliters of water, which is 10 times less. Again, this is a simplification, but I find it's useful to visualize the air as a towel that can soak up moisture. How much moisture you can soak up is determined by two things: the size of the towel and how wet it is already when you start to try and wipe things up. The size of the towel represents the temperature of the air, because like we said, warm air can hold more water. And the initial wetness of the towel represents the initial humidity of the air. So low humidity is like a fairly dry towel that still has a lot of capacity to absorb. Using this, you can now visualize what's happening every time you see some form of condensation. On a cold soda, the air outside the can is really cold, so it's like a big damp towel that has been shrunken down so much that at some point, water comes out. In the shower, the air is warm, so it's a big towel, but it's so humid the towel is fully soaked, so it loses its ability to absorb and water comes out. In the morning, you see dew on the grass because, like the soda can, the towel has shrunk and water comes out. The same logic applies to clouds or fog or to your breath on a really cold day. So for the air in your car to absorb the moisture on your windshield as fast as possible, we want a big dry towel. Knowing that, it should make a ton of sense why my experiments showed that these 4 steps will defog your windows the fastest. Number 1, turn your heater on full blast. This is because, like we said, hot air can hold more moisture, so you're increasing the size of your towel. Number 2, turn your AC on. This pulls moisture out of the air as the air passes over the cold coil. So it's like we're wringing out our towel. Number 3, make sure inside air circulation is off. Winter air is cold, and we know it doesn't hold much moisture, so if you bring it into your car and then heat it up, it has a lot of absorption capacity. And finally, number 4, crack your windows for just a little bit. This may not be possible if it's freezing cold or if it's raining outside, but cracking as many windows as possible, even for a few seconds, helps by initially exchanging the humid air in your car with the dry air from outside. Now, results will vary a bit depending on a bunch of things like the current weather, the kind of car you drive, but do an experiment and try these settings to see how much faster it is over the way you currently do it. And if these are the settings you currently use, pound it, because you're already freaking Bill Nye Science guy. If you're still having issues, you could try putting some kitty litter in an inconspicuous sock like this, and then putting it by the windshield because it will help absorb some moisture. Or you could actually try an anti-fog window treatment. So here I tested a normal windshield versus a portion of the windshield I rubbed with anti-fog liquid versus a portion of the windshield I rubbed with Jurassic Park shaving cream. And it turns out the anti-fog liquid helps a lot. However, it performed no better than shaving cream. So save yourself a couple bucks. So there you go. Hopefully you learned something new and you can shave a few minutes off your morning commute. At the very least, you'll now know this is just condensed water vapor from a jet engine. Next time a Kardashian sister uses Twitter to warn us that the government is poisoning us with so-called chemtrails.
Whoa, what did the start doing?
He's great. So yeah, so that hopefully that will actually be helpful scientific information, because the air conditioner is, the whole purpose of it is to pull humidity out of the air. So if you turn that on, it will help pull humidity out of your car air, which makes perfect sense. That's the whole point. So no, it's not an idiot talking about sublimation, but get ready, because what's happening right now north of us? A giant winter weather system and snow. And what are we gonna see? An idiot. And what's the idiot gonna show us?
Plastic in our snow.
Plastic in our snow. Have we seen this yet? Haven't seen it yet this year, but it's coming. Every time they take the snowball, they mash it up. And the more popular social media gets, the more of these idiots come out, but they pack up a little snowball and they take their little butane lighter and they light it and the snowball turns black and they're like, oh, it's plastics, microplastics in the snow. It's not. It's soot. It's soot on the snow, and the snow sublimated, it didn't melt. So sublimation, again, this is when you're going from a solid to a gas phase without melting in between. We know that dry ice is kind of our given example for that, because we see it, you know, we've probably experienced it. Anybody here never had dry ice, never played with it, never touched, never experimented with it? It's a lot of fun. If you want to do something fun with dry ice, aside from your normal typical bubbling, you have a water bottle that you can seal tightly, like a disposable water bottle, like an Aquafina or a Dasani, you know what I mean? If you can break some dry ice into small enough pieces to fit into the bottle and put like a drop of water in the bottle, screw the top on nice and tight, throw the bottle away and wait. What's going to happen? It makes the loudest bang. Like, it's a frighteningly loud bang, and it will just, because you can hear it going as it expands. You can see the little bottle expanding, and it's going to reach its breaking point, that plastic, and it will make a big loud bang. Big loud bang. It's surprising how loud it is. All right, so she's going to show you sublimation again.
Differently to different amounts of energy. So remember, we're thinking of energy as being heat. And here I have another solid, but it's even colder than my ice. This is 109 degrees below zero. This is dry ice. Dry ice is actually made out of different molecules. These molecules are made out of carbon dioxide. So we have one carbon atom and two oxygen atoms. And in its solid form, it's really, really cold. Those molecules are really close together. But as we bring it out into this room, which is a lot warmer than that dry ice, those molecules heat up so rapidly that they just skip the liquid form and they go straight to the gas. So that's a process called sublimation, the phase change. So we're going from one phase of matter, a solid, to a liquid, because we're going to get a lot of energy. It's happening really, really fast, and we're skipping that liquid altogether.
So when we're talking about enthalpy, you have to keep that in mind. That's what's going on here. Because remember, that's, I'm just bringing it back big circle, because we've seen all these phase changes before, right? Now we're talking about what's happening with the energy in those phase changes. So you have to think about, if we remember in thermodynamics, heat flows from what to what? From warm to cold. In order to get it to go from cold to warm, you got to do work, right? You got to do work. So in this case, in order to create that dry ice, in order to get it that cold, we did have to do work, because we got it well beyond what its, you know, normal natural state is. Now, this one, you may not have seen this in, you know, as close in person before, but frost forming on this metal coin is a good way to see deposition up close. So they put the coin in dry ice to get it very cold. And if you notice, her test tube clamp was doing this in the video, but you may not have been looking at it. But her test tube clamp got frost all over it because she was holding that dry ice. So if you were looking closely when she was holding that dry ice, you would have seen the same thing, guys, enough on her test tube, right? On her test tube clamp. So again, you've got deposition. And when in our case, what we're talking about is when you have gas becoming a solid. This coin is so cold because it's sitting in that dry ice. So it's 109 degrees below 0 Celsius. And because it's negative 109 Celsius, it's so cold that the water in the air is going to go straight to solid form. You don't even see the liquid. Yes.
Why is it forming most on the pod farthest away from the ice?
Well, this part is inside the dry ice. So it's the water around it. You're not seeing the water because it's in the, is that what you're asking? There's water in the air. Yes. Okay. So this water up here, why is it forming up here first as opposed to down here? Probably has to do with how it's cooling all of the air around it, which means that a lot of it's going to be sinking out and they're truthfully probably landing right on the top. If you think about it. Because those molecules are all bumping around. They did form along the sides, but those sides are also facing you. So you're looking at the little crystals that tend to form like little lines straight on, whereas this angle, you're looking at it across the top and you can see them more. So I think that's probably some of what you're seeing. All right, so to review, your melting point is the temperature, or more commonly a range, at which a substance undergoes solid to liquid phase change without an increase in temperature. When something is going through the phase change, it's not changing temperature. The temperature stays wherever the melting point, freezing point, boiling point is. At that point, the phase change is happening, but the temperature is not changing. So it's alternately the temperature at which a substance exists in equilibrium between its solid and liquid phases, which, like I said, no temperature change is occurring during the phase change. So that's why it's the equilibrium. Your freezing point is when your liquid becomes your solid. And as with the melting point, increased pressure usually raises the freezing point. The freezing point is lower than the melting point in the case of mixtures for certain organic compounds. Think back to the dry ice and think about, anybody ever seen liquid nitrogen before? Okay, so nitrogen typically floating around in gas form, right? And if you're going to put it under intense pressure by packing it into one of those big metal canisters, it's going to become a liquid, right? And then if you're going to continue to put it under pressure, it will become a solid eventually. Same thing with that dry ice. That dry ice at one point was liquid carbon dioxide. It went all the way in between, and you have to increase the pressure to get it to that point. So as you increase pressure, it's going to make it get colder and colder. Why? Why does increasing the pressure make something go from gas to liquid to solid? James? Think about the particles. The particles are moving around in the gas. You're putting more pressure on them. Do they have as much space to move? Can they move around as much? No, they're going to get to a liquid point where they're sort of slipping around each other. You keep increasing pressure. Can they move around as much? It's going to get to a point where they lock into place and now you have a solid. And then your boiling point, obviously, is your temperature, which the pressure exerted by the surroundings upon a liquid is equaled by the pressure exerted by the vapor of the liquid. Under this condition, addition of heat results in transformation of the liquid into its vapor without raising the temperature, because at your boiling point, your temperature is not increasing or decreasing. It's staying the same at your phase change point, okay? And again, that is affected by your pressure. If you go to like Denver or a city that's much at a higher elevation, you'll see sometimes your recipe instructions are different, and your boiling point is going to be a little different, right? All right, so let's review these three one more time. Make sure we understand.
Boiling point.
This guy's got an accent, but he's good.
Water freeze or melt at 0 degrees centigrade. Before starting the lecture,
So is it freezing or melting at 0? What's happening?
And get access to our 100 of unique and simple lectures for free. Firstly, let me teach you fundamental universal fact. If you increase the temperature of any substance, the motion of molecules increases. If you decrease the temperature of any substance, the motion of molecules also decreases. Thus note it down that There is direct relationship between temperature and motion. Now, what is melting point? Well, consider ice. Let the ice is present at minus 10 degrees centigrade. The microscopic description of ice reveals that all the molecules of ice are closely packed together in a regular pattern. The molecules of ice only vibrate about their mean position and never break up the pattern. Now, if you add heat energy to the ice, its temperature increases. We know that when temperature increases, the motion of molecules also increases. If you keep increasing the temperature of ice, the motion of molecules also increases. At 0 degrees centigrade, the motion of molecules become enough that they start moving apart and become liquid or water. Remember that temperature at 0 degrees centigrade remains constant until all the ice is converted to water. Once all ice is converted to water, temperature then increases. For example, temperature may increase to 5 degrees centigrade. Now listen carefully. The constant temperature at which a substance changes from a solid to a liquid state is called melting point. Let me repeat it. The constant temperature
Keep repeating
at
it, just
which
in case
a
you didn't hear it.
substance changes from a solid to a liquid state is called melting point. The melting point of water is 0 degrees centigrade. Because at 0 degrees centigrade, the ice converts to water. Thus, remember that melting point is the temperature at which a substance converts from a solid to a liquid state. Now, what is boiling point? Well, consider water at 5 degrees centigrade from the previous slide. The molecules of water slide over each other, or you can say that molecules of water are in random motion. I add more heat and increase the temperature. Increasing the temperature means that increasing the motion of molecules. Now at 100 degrees centigrade, the motion of molecules is maximum, and adding more heat to it break up the molecules from one another. Finally, water is converted to steam. Here, the temperature remains constant at 100 degrees centigrade until all the water is converted to steam. Once all the water is converted to steam, temperature then increases. For example, it may increase to 105 degrees centigrade. Now listen carefully. The constant temperature at which a substance changes from a liquid to a gaseous state is called boiling point. Let me repeat it.
Again.
The constant temperature at which
He likes to repeat this
changes
point.
from a liquid to a gaseous state is called boiling point. The boiling point of water is 100 degrees centigrade because water converts from liquid state to gaseous state at this temperature. Thus remember that boiling point is the temperature at which substance changes from a liquid to a gaseous state. Now what is freezing point? Well, consider water at 40 degrees centigrade. We can extract heat from the water by
We'll
pressing
skip him ahead because you know what he's gonna say.
it's near a liquid state to a solid
A liquid thing.
until all the water molecules convert to ice. Once this happens, the temperature starts for
So here he gets to
liquid
repeat it.
state to
Repeat
a
this,
solid
right?
state. It's called freezing point. Let me repeat it.
Repeat
The constant
it.
temperature at which a substance changes from a liquid state to a solid state is called freezing point. Note it down that the freezing point of water is 0 degrees centigrade. Thus remember that freezing point is the constant temperature at which liquid becomes solid. Finally, let me teach you a bonus question.
Here's
Why
the point.
0 degrees centigrade is both the melting point and freezing point of water. Or does water freeze or melt at 0 degrees centigrade? Well, at 0 degrees centigrade, if you increase the temperature of water or you add more heat energy to water, it is called as melting point of water. While at 0 degrees centigrade, if you decrease the temperature of water or you extract more heat energy from the water, it is called as freezing point. Thus noted down that melting point and freezing point of any substance are the same depending on addition or extraction of heat. I hope that you have understood the concept of
That was the
melting
point. It took him a while to get there. Yes,
It's avoiding
yes. Yes,
every YouTuber.
yes. So, guys. So yes, PJ just made a good metaphor. It's like the cup half full, cup half empty. It depends on what you're doing to it. So if 0 Celsius is freezing point, 0 Celsius is melting point. It depends on whether you're adding or extracting energy, which again has to do with our enthalpy situation. Yes. Then it's sitting there at both freezing point and melting point, because that's when it's in, you know, it's that's
seems
the
like-
phase change.
That seems like it'd be a paradox.
A paradox. There's a lot of those. So surface tension. All right. So surface tension. Whoop, no, wait. Hold on, you. So surface tension is your attractive force exerted upon the surface molecules of a liquid by the molecules beneath that tends to draw the surface molecule into the bulk of the liquid and makes the liquid assume the shape having the least surface area. When you put liquid in a graduated cylinder, you have your meniscus that goes this way because it is the least surface area. It's trying to pull it down. It doesn't go like that, does it? Right? But a water droplet does. When you put a water droplet on a table, it ends up forming a dome because it's only touching one other surface, which is what's beneath it. It's not got walls around it that it's trying to creep up. So that has largely in water to do with your hydrogen bonds.
Welcome to a Mad Scientist production of Surface Tension, in which we will look at how intermolecular forces affect the surface of a liquid. So what is going on at the surface of a liquid? Let's take a look by shrinking to the nanoscale. So here we are looking at the individual molecules in a liquid, and let's say that each blue circle represents a molecule of water. Due to kinetic energy, the particles that make up a liquid are in constant random motion, and so they will have a random arrangement. You might expect the particles at the surface at the micro level to form a random surface as shown here. But what we should find out is how do intermolecular attractions influence the surface? First, let's look at intermolecular forces under the surface, where attractions of individual molecules pull on each other in all directions. At the surface, pull on the molecules is lateral and downward. There is negligible attractions above the molecules, and so the net force on surface molecules is downward. The result of this downward force is that surface particles are pulled down until counterbalanced by the compression resistance of the liquid. Surface molecules are compressed more tightly together at the surface, forming a sort of skin on the surface with less distance between them compared to the molecules below them. Surface molecules also form a much smoother surface than one would expect from randomly moving molecules. What do you think surface tension would do to a liquid not confined in a container? In this model of a small water droplet, what is the net direction of the force on the surface molecules? That's right, it is toward the center. And so a free-falling drop of liquid takes on a spherical shape. Here we see water dripping from a faucet. If this does not look familiar to you, turn on your faucet at home with very little pressure and see what happens. Or do an internet search for the behavior of water in zero gravity to get a great view of surface tension. Water in particular has a very high surface tension. Do you know the reason for this? What creates the attraction between water molecules? In looking at an individual water molecule, we can see the particularly strong attraction between the oxygen and hydrogen due to their opposite charges. Hydrogen has a strong partial positive charge and oxygen a strong partial negative charge. This strong attraction occurs between many water molecules close by. The strong partial charges result in a strong attraction between water molecules called hydrogen bonding. Interestingly, there are creatures that have evolved to take advantage of water's high surface tension. The water strider is a common insect that you may have encountered. What adaptation in their feet has occurred to take advantage of water's surface tension? Think about it. See ya.
So I got this video last night and I'll walk with my phone to show you because I didn't get a chance to put it in slideshow, but it's a perfect example of why that works. This is a whole colony of ants walking on top of a stream to cross, making a bridge out of other ants.
Oh, I've seen that.
And it's pretty wild. They are like, there's some of them are floating and the others are walking on them. And they're just walking along, making a little ant bridge.
They got places to be.
Yeah, they got places to be. This guy's like, tell me, what magic do they use?
I'd like a water strider.
But I love the guy. The guy is so impressed. He's like, can you imagine this? What kind of magic do they use? Hydrogen bonding. Yes. I think they just slowly make their way out. Like they probably grab each other and pull each other out like a rope. I don't know. Uh-huh.
So I know you.
Uh-huh. Shh. Guys, stop. Uh-huh.
If you take a spoon and fill it with water as much as you can, the sides of the water will just like suddenly stop.
Mm-hmm.
So it'll look like it's being stopped by a wall, but there's nothing there.
Right, exactly. And that's the surface tension you can see. So our intermolecular forces, which we can say as IMF usually, because we don't talk about intramolecular forces in this case often enough to abbreviate them, or secondary forces, are forces which mediate interaction between atoms, including forces. This are in your notes if you're checking your definitions. Including forces of attraction or repulsion, which act between atoms and other types of neighboring particles. Intermolecular forces are weak relative to intramolecular forces, which hold the molecule together. Molecules are more tightly held as one molecule than they are from one molecule to another molecule. London dispersion, I'm giving you your definitions here, so check them. London dispersion force is a temporary attractive force that results when electrons in two adjacent atoms occupy positions that make the atoms form temporary dipoles. Dispersion forces are present between any two molecules, even polar molecules, when they are almost touching. Dipole-dipole are attractive forces between positive end of one polar molecule and the negative end of another polar molecule. Hydrogen bond, a special type of dipole-dipole attraction between molecules, not a covalent bond to a hydrogen atom. It results from the attractive force between a hydrogen atom covalently bonded to a very electronegative atom, such as nitrogen, oxygen, or fluorine atom, and another very electronegative atom. So here are the forces all together again. This one was cuter than the others. I like the little old lady with the vacuum. Yeah, she kind of looks like the queen, doesn't she?
And I saw the
Were failed, the guy in 17C took his shoes off and someone spent the entire flight crying. I'm looking at you, Dad. After 10 hours in the sky, the Dalton family finally made it to England. So let's use their international destination as an opportunity to cover intermolecular forces. Intermolecular forces are electrostatic interactions between molecules. In contrast, intramolecular forces are interactions that hold together atoms within a molecule. There are a number of intermolecular forces, but we're going to cover the three most high-yield ones here: London dispersion forces, dipole-dipole interactions, and hydrogen bonds. For London dispersion forces, let's check out this red double-decker bus, an iconic way to see the sights of London. London dispersion forces are a type of van der Waals interaction that are caused by random fluctuations in electron density. You see, because electrons are constantly in motion, they can become unevenly distributed. This uneven electron distribution can make one side more negatively charged and the other side more positively charged, which creates a temporary dipole. Then the transiently negative end of the atom or molecule causes one side of a neighboring molecule to become more positive, and that positive end causes yet another end of a neighboring molecule to become more negative, and rinse and repeat. Anyway, you can remember that London dispersion forces are created by a temporary uneven electron distribution with this uneven distribution of bubbles. And you know what bubbles are? Temporary fun. Seriously, the little Dalton really should have sprung for the silly string. Next,
take a look at the larger flag on the big tour bus and the smaller flag on the very Mini Cooper. This should remind you that London dispersion forces are stronger in larger atoms and molecules and weaker in smaller atoms and molecules. This should make sense. When electrons distribute unevenly, the difference in charge between the partially negative side and the partially positive side is greater in atoms and molecules with more electrons and more protons. Said another way, large atoms and molecules can become more polar, though this polarity is temporary, because they have more charged particles. Unlike dipole-dipole interactions and hydrogen bonds, London dispersion forces are experienced by all atoms and molecules, even nonpolar molecules, which is why this bus tour is all-inclusive. Yup, they even include tickets to Buckingham Palace to harass the guards. Dad is gonna love that. Well, it's not a trip to England without buying a bottle of yeah, never mind. And actually, it looks like this bus ad is marketing the knockoff brand anyway. Let this bottle of weak sauce remind you that London dispersion forces are the weakest of the intermolecular forces. Weak sauce. All of the price, none of the flavor.
Weak sauce. There's your London dispersion. So I don't expect you guys to be able to do tons of this, but I want you to understand there is a way to determine which forces are working within compounds. Okay. So I know today's lots of videos, but it's lots of very small concepts that you have to like, well, big, but microscopic.
Even here.
Hey guys, it's Michael from Chemistry. In today's video, we'll be talking about how to determine which IMF or intermolecular force a substance has. Let's start with the definition of IMF. Intermolecular force is defined as the attraction between molecules. For example, I have two water molecules right here. The attraction between one water molecule and another water molecule is called the intermolecular force. That's in contrast with the bonds between the O and the H. These right here, these are bonds, they're covalent bonds. These are called intramolecular forces or just bonds. So intermolecular forces are attraction between molecules, and that's different from the attraction within the molecules or the bonds. The three main intermolecular forces that you'll need to know in most chemistry classes are London dispersion force, dipole-dipole, and hydrogen bond. So how do you determine which of these forces a compound will have? Well, you can just use this guideline. If a compound is nonpolar, then it will have London dispersion forces only. If a compound is polar, it will have London dispersion and dipole-dipole. And then lastly, if you have a compound with an H that's directly attached to an F, an H directly attached to O, or H directly attached to N, then we'll have all three. We'll have London dispersion, dipole-dipole, and hydrogen bonding. So everything, all compounds have London dispersion. If it's polar, it'll also have dipole-dipole. And then if it has HF, HO, or HN, then we'll have dipole-dipole and hydrogen bonding. So let's take a look at some example problems and apply these rules. This problem, we have to determine what IMFs are present in the following substances. The first substance is carbon dioxide. To do this, we first have to determine if the compound is polar or non-polar. And to do that, you have to draw the Lewis structure. I'm just going to draw the Lewis structure to save time, but if you're having trouble drawing the Lewis structure, check out the video in the description below where I go over that detail. The Lewis structure for carbon dioxide looks like this. C with double bond, and then each of the O's have two lone pairs. Then we have to check whether this compound is polar or non-polar. And to that, we can just use a quick checklist. I have a video where I go over this in detail, but for saving time, I'm going to type out this checklist right here. So compound being non-polar if the central atom, the middle atom has no lone pairs, and all the atoms surrounding the central atom are the same. You can see carbon meets criteria number 1, because carbon doesn't have any lone pairs on it, and it also meets criteria number 2, because both surrounding atoms are oxygen. So that means that carbon dioxide will be non-polar, and since it's non-polar, it means that it only has London dispersion forces. So we'll start once again with the Lewis structure, and the Lewis structure SF4 looks as such. Then we need to determine whether this molecule is polar or non-polar. So we use checklists. We see if the central atom has any lone pairs. And S does have a lone pair in the central atom. So since it doesn't meet this first criteria, then this compound is going to be polar. And since it's polar, it will have London dispersion forces and dipole-dipole. It doesn't have hydrogen bonding because we don't see any HF, HO, or HN in this compound. Okay, next example, CH3, NH2. Just right off the bat, you see that there's an N and an H right next to each other. So that means this compound means it has an N and H, which means it's going to have lens dispersion, dipole, and hydrogen bonding. So if you see HF, HO, or HN in the molecule, then you know it's going to have all three. Next example, C5H12. Here's a neat trick. So any compound containing carbon and hydrogen only is going to be nonpolar. So since C5H12 only has carbon and hydrogen, it's going to be nonpolar, which means it will have lens dispersion forces only. Other examples of this be like C4H10, C20H40. So any compound that just has carbon and hydrogen will be nonpolar, meaning it will only have lens dispersion forces. Next example, neon. This is a single atom, a single element. So if it's a single element, then it has to be nonpolar. And since it's nonpolar, it will only have lens dispersion forces only for neon. And then lastly, HCl. We draw out the Lewis structure for HCl. It looks like this. And we know that Cl is more electronegative than H, which means that you're going to have a dipole moment pointing in this direction. And so that makes it polar. And if it's polar, it will have lens dispersion forces and dipole, but it doesn't have hydrogen bonding because we don't see HF, HO, or HN.
You see how we drew the arrow? That's, well, I don't. When you draw this, that shows the dipole moment. So in this case, he's showing that the polar end is over here, and this is the positive end because you see the electrons are all on this side. So that's what that arrow means.
And that's how you can determine what type of intermolecular force a substance has. The first step is just to draw the Lewis structure, then determine if it's polar or nonpolar. So once again, I went over that pretty quickly to save time, but I have videos that teach you how to draw Lewis structures and determine if it's polar or nonpolar in detail. And if a compound has HF, HO, or HN, then that means it has hydrogen bonding, dipole, and lens dispersion force. If you want to learn how the ACE can...
No! He does have good videos, but he's loud. All right, so new year, new you, right? Everybody's gonna be good about handing in assignments on time, getting labs in on time. New year, new you. Woo! Everybody's gonna do their binder work before class. New year, new you. Okay, because I had time during lab today, your forums are already established. I tagged everyone I could tag. Some of your names don't pull up when I try and tag. So it could be because I don't know what you call yourself. I've been through this before, but like some of you have weird screen names and I can't guess what they are. Not a clue. So be aware of that. Does anybody have any questions about second semester Q2, how your grades average? Somebody asked a good question, juniors. I'll point it out real quick just in case you didn't catch it. But on your report cards, you have a Q1 average, a Q2 average, and a semester 1 average. The midterm is not included in the Q2. That is before you took your midterm. The semester average is Q1, Q2 plus midterm. So if you're wondering like why it looked the way it looked, like somebody was trying to calculate it and couldn't figure it out, that's why. The same thing will occur. You'll get Q3, you'll get Q4, and then you'll get final, which will be Q1, Q2, midterm, Q3, Q4, final. Got it? Cool. I'll show you this real quick. I put a different utensil in here because that God bless it, that ladle really needed some scrubbing. So I put this little spreader in, and you can absolutely see where the line of the water, you can see where the water stopped. Like, see the nice line right there?
Have you decided if we could do groups of 3 for
Groups of 3 for fine. Who are you looking to group up with?
Yeah.
It's you for in.
Yeah.
What's your element?
Neon.
Neon.
I have a coin.
Wait, I'll let you
Will you pass me my coin? I also have one coin.
Have a look at it. You can see right where the water level is.
Sure. As a singular.
I'll take Goose coin. Where's Adrian? Oh, the James is on it. I'll take Goose coins. Sorry, I'll cook it. You're too late. So I'll take PJ's again. Take PJ's. Yo, you took your
You can really smell the sulfur on those. Like it's really sticky.
Did I not have coins? Well, who's the all coins? I answered like 3 questions.
No, you're not taking any out of there. Too bad.
Best way to do it though is solar power. That's this stuff right here. It goes straight. Solar power works like insurance. Cause that's a real straight chemical reaction.
One of them just gives my bad vibes when he gets loud. Also, I just don't want to, because I like nuisance and I was careful. No. Why? The amount of times that I have created things to get out of that, it's crazy. I will keep doing it. But it was probably.
You have a good New Year? Yeah?
I got this.
New year, new hair, new, okay, what is?
It's a
Blanket hoodie. It's a snuggie essentially.
What?
When somebody from youth group brought a Cheetos snuggie, it looked like a Cheetos bag, it became the white elephant. It was the one they were fighting over, it's funny. It really was something for 2 of them, I guess. Because 2 kids showed up with them, and they were in different boxes when they got unwrapped, and you never know what it's gonna be until it's unwrapped, right? And then that was funny. Was it good having been back home, or just weird? Cool. She said she could share.
He did, yeah, he said it. I look like a box. The closer you come my head, where is my hat?
Backpack, right? I made the heck out of these last time. Thank you, James. That is very sweet of you. Are you getting some? I see that cup though. Yeah. Yeah. This is so good. Oh my gosh, thank you. Tell your mom big thanks. Thank you. I know they took forever. You're getting excited? Yes. Everything's looking like it's finishing up and finalizing and you're about to go on with your life. I will tell you from experience, because you're gonna be living away. When you come home, expect the first 2 weeks to potentially be a living hell. And then it will get to normal, but it's just because you've been on your own and they've been without you and it's gonna be weird, but like when you come back next May, it's gonna kill you, and you don't kill them because that one up there never died. And so, behind my hand. But it's all good, you know, it's great. I'm excited for you. It's a good fit for you, I think, and you're gonna enjoy it. You're gonna really enjoy it. Well, thank you, that was very sweet of you. I never mind writing reviews, certain recommendations. He's done, he's going to college next year. This is his last semester in school. He is almost done. And then he's going to leave us for brighter horizons.
What college?
Barry. You seen, ever been to Barry? Beautiful campus. Beautiful. Yes, it's in Georgia. It's a small private school. It's really, really pretty. It's a lot of the buildings are really old and they have deer everywhere. The campus is absolutely full of deer. I don't know why, but there are deer everywhere. Do you know why, James? Why there's so many deer? It's weird though, like when you drive over the campus, it doesn't matter, middle of the day, there are just deer. Everywhere, it's wild, like, I don't know, maybe, you know what you'll like, stop this, is recording. So for Christmas, I got a bird buddy. Have you ever seen these?
Is it, you mean right there?
Yeah, you see it? This is right up your alley. I was gonna say, this is right up your alley. Come on and close. Close. Why are we closing? So like